We're first being asked to complete the square on this function, so f of x, first thing I'm going to do is factorize the 2 out of the first two terms, x squared plus 2x. Okay, and then complete the square on x squared plus 2x. So this becomes x plus 1 squared minus 1 plus 9. Just a reminder on how this actually works. We have a rectangle. It's x plus 2 times x. That gives me x squared plus 2x. That's the bit I'm focusing on here. And I can split this into a square and a 2 by x. But I'm trying to complete the square. So what I actually do is split this into a half. So it's 1 by x, and I get rid of it, and I move it down here. So then this is, they're both x plus 1 now, except, so actually what I have is x plus 1 squared, but I've got a little bit missing, this bit here, which is a 1 by 1 square. So that's where it comes from, and that's how you learn to kind of just have the x term, put it in a bracket, and then you minus whatever that number squared is every time. But that's why it works. Okay, expand it back out. 2x plus 1 squared minus 2 plus 9. I'm going to get plus 7 overall. Then asked to sketch this function essentially, showing any points of intersection with the coordinate axes and the coordinate of any turning point. So I'll do it down here. Okay, right. First thing is that it's going to be a happy quadratic. It's a positive x squared curve. It's going to go through the y-axis at 9. So x equals 0, y equals 9. And then actually it's not going to have any roots when y is 0, because if I set it equal to 0, I'll get minus 7, and I can't square root minus 7. This is the minimum point is actually going to be minus 1, 7. Okay, that's going to be my turning point. Because this thing here is always bigger or equal to 0. The smallest it could be would be 0, which gives me my minimum value of 7. And that will occur when the bracket is 0, so when x is minus 1. So you just swap this one round and then take that one. Minus 1, 7 takes me about here. And then I've got my happy quadratic and then the 9 that we found from the y-intercept. So that is a pretty good sketch. Next up, we're asked to describe fully the transformation that takes f of x onto this curve g of x. Now, it doesn't look like a great mapping at the moment. Definitely not from here, but also not from the completed square form. So the first thing I think to do is expand everything out, and that 4x is the complication really. So kind of expand it out, absorb the 4x, and then we'll go from there. So it will be 2, and then x squared minus 4x plus 4 when I expand that double bracket, plus 4x minus 3. That's 2x squared minus 8x plus 8 plus 4x minus 3, which gives me 2x squared minus 4x plus 5. Okay, I need to complete the square again now. So in this very similar way to before, take the 2 out. I'm not going to rush it actually. X squared minus 2x plus 5. And 2 x minus 1 squared minus 1 plus 5, giving me 2 x minus 1 squared minus 2 plus 5, so plus 3. So I've managed to turn it into something that's now in completed square form, and it's going to be much easier to see how to go from here to here. So it might help we've got f of x, to write down what g of x is in terms of f of x. Now, instead of adding 1, I'm minusing 1. So I'm actually doing x, and then I'm minusing 2. That would give me 2 lots of x minus 1 all squared plus 7. Okay, I want a plus 3, so I need to then minus 4 from it. And therefore, this is a translation by 2 in the x direction, and then minus 4 in the y direction. I can write that really nicely just as a vector. Translation by 2 minus 4. Finally, we've got a question on the range of this function here. It's 21 divided by our original function. I'm just going to write it in a couple of different forms. 21 over f of x, or 21 over 2, and I forget what it was written like in completed square form, x plus 1 squared plus 7. Now, the first thing to say is that remember, f of x was always positive. We drew a sketch of it, and so h of x is always going to be positive as well. But it will approach 0 as we approach infinity. For our f of x, it will approach 0. So actually, that's going to be part of our range. The minimum, there is no minimum as such, but it's going to be like an asymptote going towards 0. In fact, I'm going to start drawing it. It would look like this either side. And so it's now just about the maximum. Maximum h of x is going to be when f of x has its minimum. And that is when x is equal to minus 1, giving f of x equal to 7. So max hx is going to be 21 over 7. That was the minimum value of the quadratic, so the maximum value of hx is actually 3. And it's going to end up peaking there, so it's going to look a bit, I mean, it will be symmetrical. I haven't quite drawn it symmetrical, but that is roughly what my h of x would look like. Okay, you're not necessarily expected to sketch it. I'm just drawing it here to try and explain to you where these values are coming from. Okay, because I'm doing 21, I mean, you can almost forget about the 21 and do like 1 over and just times by 21 at the end. When you do 1 over a function, as it goes off to infinity, 1 over the function is going to go off to 0. And then if that one has a minimum at minus 1 and it's 7, then the other function is going to have a maximum there, and it's going to be 1 over 7. But when we times by 21, we'll get to 3. Overall, then, our range is going to be h of x is bigger than 0, has to be, but it's going to be less than, I should say less than or equal to 3.